Hello, my name's Christopher Heel, and I'd like to thank you all for coming to the talk today. I'd also like to thank Kumal for inviting me to give this talk. I predominantly study small-scale, short-period gravity waves using high-resolution modelling, and I wanted to talk to you a little bit today about gravity waves and hopefully give you an intuitive overview and understanding of their processes. So this is the contents of the talk here. I'll start by describing what a gravity wave is and then why we care about them. I'll then briefly go through how they are studied in terms of instruments and models. Then I'll go through the gravity wave life cycle and finish up with some of the current problems in gravity wave research. So let's start by talking about what is a gravity wave. Crudely put, they can be described as wiggles in the atmosphere, and in fact this is what Colin Hines described them as in his original 1960 paper. They were irregularities and irregular motions in the upper atmosphere, and this can be seen from the figure on the right hand side, which shows a wind profile with altitude. There's a mean wind with wiggles or gravity waves superimposed on top of them, and this initial 1960 paper provided the framework and theory to study these wave motions. So gravity waves are actually driven by a balance of forces. They're created by perturbations to a stably stratified atmosphere, which are then restored to equilibrium by the forces of buoyancy and gravity. So the atmosphere is stratified by density, and what this means is that the density is constantly decreasing with altitude. So if an air parcel is lifted from its equilibrium position, it will find itself surrounded by less dense air, and then gravity will tend to pull that down back towards its equilibrium. However, it will shoot its equilibrium position, and then it will find itself surrounded by regions of denser air, and it will be driven back up by buoyancy, and you get an oscillatory motion. The energy from these oscillations are carried away in the form of waves, and these are gravity waves. And the figures in the bottom right here just show some indication of wave motions in the lower atmosphere. So for a more formal definition of gravity waves, we begin with the inviscid Navier-Stokes equation, which represent conservation of density, momentum, and energy respectively, with the energy partitioned into the internal energy and the kinetic energy. We then assume that the state variables are made up of a linear combination of a mean background state and a wave-like perturbation of the quantity. So you can see that our U vector here, which represents the wind, is made up of U, which is the zonal wind, V, which is the meridional wind, and W, which is the vertical wind. Then we also have the pressure and the density. So the overbar state represents the mean state, the background state, and the primed quantity represents the wave-like perturbation. And the wave-like perturbations are made up of some yet unknown function of altitude, or Z, and then a wave-like solution in x and t, which is given by the e to the I kx minus omega t. So we take these form of the state variables and then we plug them into the Navier-Stokes equations, do some algebra and rearrange, and we end up with the Taylor-Goldstein equation. And this provides a description of the vertical velocity amplitude of the gravity wave in terms of m squared, the vertical wave number. The solution to this is just a wave-like solution, e to the I kx plus or minus mz minus omega t plus z over 2h, and we'll talk about that term later. But what is crucial is that these waves are dispersive, and they have a dispersion relation, which describes how the wave parameters relate to each other and to the background atmospheric parameters. So just to describe this in more detail, m squared represents the vertical wave number squared, k squared represents the horizontal wave number squared, n squared is the buoyancy frequency of the atmosphere squared, which is proportional to the density and temperature gradient of the atmosphere. Omega is the ground relative frequency of the wave, and U bar is the local horizontal mean wind. So the denominator of this equation, the omega minus uk, is known as the intrinsic frequency, and this is the frequency of the wave in the frame of the relative mean wind. Cp is the normal definition of the phase speed, omega over k, and then you have the group velocity, d omega by dk, or dm for the horizontal and vertical group velocities respectively, and this describes the direction of propagation of the wave packet and also the energy propagation direction. It's key to note that it's this dispersion relation that makes a gravity wave a gravity wave. If you see a gravity wave in the atmosphere, it has to fit this dispersion relation in order to be a gravity wave. So this really is a key concept in describing gravity waves. I'll now describe some of the important characteristics for gravity waves. Firstly, the amplitude grows exponentially in altitude, so the density decreases with altitude, and gravity waves conserve energy and momentum, which is proportional to this decrease in density. Thus, the amplitude of the wave must increase with altitude. Also, gravity waves are bound by the buoyancy frequency of the atmosphere. So the buoyancy frequency is the natural oscillation frequency of the atmosphere if a parcel is lifted vertically from equilibrium. And it's proportional to this theta term, which is the potential temperature, but it's essentially equal to the proportional to the gradient of the density. The n squared term gives information on the stability of the atmosphere. So if n squared is positive, the atmosphere is stably stratified. If it's equal to 0, it is neutrally buoyant, and if it's less than 0, then the atmosphere is locally unstable. It also represents the highest frequency at which a gravity wave can exist, and on average is about 5.5 minutes for the atmosphere. Also, the wave parameters, in particular the frequency, can determine the propagation angle of the wave to the ground. So if the frequency is high, then you tend to have more vertical propagation of the wave, and if the frequency is low, then you have more horizontal propagation of the wave. Another important characteristic is that the phase velocity of gravity waves is perpendicular to the group velocity. So as the whole packet moves upward in the direction of the group velocity, denoted by the red arrow, the vertical phases are actually moving downward in the direction of the blue arrows. So here's a schematic representation of wave propagation. You can see this wave is propagating up and to the right in the direction of the red arrow, or the group velocity, where the phases are moving down and to the right in the direction of the phase velocity, the blue arrow. There's also a set of polarization relations which define the amplitude and phase relations between the atmospheric parameters for gravity waves, and you can see that these are often dependent upon the relative values of k and m, so the horizontal and vertical scales of the wave. Gravity waves can also be highly dispersive, and you can see that it's very hard to distinguish a single packet in some cases. You can see in this figure here that by 100 seconds, which is on the x-axis, the packet actually spans 100 kilometers in depth. So it's difficult to define a single wave when you have it spread out over the whole atmosphere like this. So when we're talking about gravity waves in the atmosphere, we expect them to have horizontal wavelengths between 10 and 1,000 kilometers, and vertical wavelengths between 5 and 40-ish kilometers. Their periods are likely to be bound by the buoyancy frequency, so a few minutes at the low end to several hours in the high end. It's also crucial to note that the gravity wave spectra will vary considerably with altitude because of variations in the background wind and temperature structure, which will filter these waves as they propagate upward. So why do we care about gravity waves? Well, gravity waves are a primary mechanism for carrying energy and momentum away from a source region in the lower atmosphere and distribute it throughout the rest of the middle and the upper atmosphere. So this Fritz and Vincent paper in 1987 states, our analysis reveals that over 70% of the momentum flux and inferred zonal drag was due to gravity waves with observed periods less than 1 hour. So how does it do this drag on the atmosphere? Well, this is done by this term, the momentum flux divergence or body forcing. So the momentum flux is highlighted in red, and this is conserved for a non-dissipating gravity wave. But when a gravity wave dissipates, it deposits its energy and momentum into the background flow and will accelerate or decelerate the mean flow locally. Equally, from a divergence of heat flux or from viscous damping, it can create a heating or cooling of the atmosphere and change this temperature structure also. So through the deposition of its energy and momentum, gravity waves can influence the thermal structure, transport constituents, provide mixing and circulation of the atmosphere through these dissipation and wave breaking processes. One consequence of this is the quasi-biennial oscillation, and this is a 2-yearly reversal of the mean zonal winds in the tropics caused by directional forcing of gravity waves over time. Another is the general circulation of the atmosphere. So gravity waves contribute highly to the Brewer-Dobson circulation, which is a summer to pole circulation in the stratosphere, and also primarily drives the mesospheric circulation. So under thermal conditions, you'd expect the summer mesopoles to be the warmest part of the mesosphere, when in fact it's the coldest. And this is due to gravity wave forcing, which generates a mean circulation with a lifting of the air and adiabatic cooling of it at the summer pole. But fundamentally, we cannot accurately predict weather and climate without understanding gravity waves. Gravity waves are unresolved in general circulation models, and they need to be parameterized. And these parameterizations use very simplified physics, which have a lot of problems. For example, they constrain all gravity waves to the grid cell that they're generated in the model. They have instantaneous propagation from their source to their demise. They have no consideration of nonlinearity, and they also essentially tune the parameters of the sources so that the observations look right rather than based upon physical arguments. So how do we observe gravity waves? One method is in situ measurements from aircraft, balloons and rockets, and these will typically measure the state parameters such as the pressure, the temperature, the atmospheric constituents. Another method is imagers. And these imagers often measure the perturbations to the air glow in the upper atmosphere through the hydroxyl bands at 87 kilometers, the atomic oxygen green line at 95 kilometers, and the atomic oxygen red line between 200 and 250 kilometers. LiDAR is another popular way of measuring gravity waves, and this provides a altitude time profile of the wind's temperature and density in the stratosphere and mesosphere, depending on the type of LiDAR that you're using. Radars provide another popular measure of gravity waves. This can be done through various radars, and you can measure from the troposphere up into the ionosphere, in fact, using these different radar methods. Satellite is also really useful for looking at global coverage of gravity waves. However, you struggle to get good temporal resolution because of the satellite passes and how fast they're passing over. So this image at the bottom shows the ERS imager upon the NASA's Aqua satellite, and you can see these gravity waves in the stratosphere over the United States. The total electron content can be measured by GPS and GNSS networks, and this will measure a manifestation of gravity waves in the electron density. And these are actually known as travelling ionospheric disturbances, but they are manifestations of gravity waves in the ionosphere. So when we talk about models, there are three main types of models. The first are local models, and these are concerned with explicitly resolving all of the gravity wave processes and the turbulence processes as well. So the direct numerical simulation will resolve all scales down to the smallest turbulence scale, whereas a large eddy simulation will typically parameterize part of the turbulence spectrum. So these are very high resolution localized runs with resolution in the order of meters and temporal resolution of seconds and a range of seconds to a few hours. The second type of model are numerical weather prediction models. These are your typical forecast type models. These are much larger in scale and as such have larger resolution. So their resolution is the order of tens of kilometers, and the temporal range is approximately days at 3 hourly intervals. So these will resolve part of the gravity wave spectrum, but also another part below the resolution of the model will need to be parameterized. And parameterization is just a simplified description of the physics and how they will affect the atmosphere in general. The third class is a general circulation model. This is a large-scale global model concerned with predicting climate. The resolution of these is much lower, so they are typically an order of a degree, and their temporal range is years. So in these models, gravity waves are almost exclusively parameterized, and these parameterizations are incredibly simplified. So all gravity waves are confined to the single cell. The propagation is instantaneous, and also there's no nonlinearity included in these parameterizations. You need to specify the source spectrum as well, which at the moment is not particularly well constrained. So there's a lot of problems with these gravity wave parameterization, and it's an ongoing area of research. So we know that gravity waves are born from displacements of the atmosphere at periods greater than the buoyancy frequency. But what are some of the main sources? So one of the main sources, in fact, is topography. So as the wind flows over mountains, it is lifted, and as it's lifted, it gives rise to these gravity waves, these propagating gravity waves. And you can see an example of that in the figures on the right. A second large source is convection, so this is from lifting of the air from thunderstorms, hurricanes, tornadoes, and any large-scale storm system really. You can see in this figure these concentric waves in the mesosphere in the black and white image with the thunderstorm superimposed in colours and below. Some other sources, geostrophic adjustments, are basically when there's an imbalance in the flow and the imbalance acts to correct itself. The energy from that correction can be turned into gravity waves which propagate away. Also natural hazards such as tsunamis, volcanoes and earthquakes can cause gravity waves, as well as man-made sources such as bombs, rockets and mining explosions. So let's talk a little bit more about mountain waves. So if we imagine a steady horizontal flow over a mountain where the mountain height profile is given by h of x, we know that the flow must be parallel to the mountain, and so the air is lifted over the mountain, and the vertical velocity can then be described by the horizontal flow times by the gradient of the mountain profile itself. And it's this lifting, this vertical lifting of the air, which gives rise to the gravity waves. There's two things to note about mountain waves. Firstly, they're stationary, and this means that they have no ground relative frequency. You'll see their phases do not move over the mountain. Secondly, a mean wind must exist at all altitudes for them to propagate. So if that wind goes to zero at some altitude, then the wave will cease to exist and actually be critical level filtered and absorbed into the mean flow. So I'd just like to show this 3D mountain wave simulation in WRF from Chris Cruzy. Here we have a constant background wind of 30 meters per second at the source, and then we have a mountain which is 200 kilometers wide and 1,000 meter tall and defined by a simple cosine function. The left hand panel here shows the distance on the x-axis and the height on the y-axis, and you'll see this gravity wave start to propagate. You notice its phases are not moving, they're constant, and then the wave will break at some altitude and start to dissipate away. So I'll move on to talk about convectively generated waves. There are three main proposed mechanisms for these generations. The first is by latent heating. So as the moist air in a thunderstorm is converted to rainfall, this generates a latent heating which provides the energy to generate the gravity waves. Second is the mechanical oscillator effect. So as the air in a thunderstorm rises, it will impinge on the tropopaules and start to oscillate about the tropopaules because it can't rise into the stratosphere, and this oscillation will generate gravity waves. The third is the obstacle effect, which suggests that this thunderstorm blocks the mean flow, which then has to be redirected over or around the thunderstorm, and this lifting generates gravity waves. In reality, all three of these mechanisms are present and linked via the nonlinear advection term in the Navier-Stokes equations. So I'll just provide a simulation here of a convectively generated wave from a single plume. So on the left hand side you've got a horizontal slice of the atmosphere at z equals 85 kilometers, and on the right hand side you have the zonal distance on the x-axis, the altitude on the y-axis, and you'll have this this blue line represents the mean wind. So you'll see, if you look at the right hand figure, you'll see this plume go off at the bottom, and then the gravity waves will start to propagate up and fan out. There'll be a preferred direction, and then eventually you'll get this wave break-in form, which you can see in the left and the right hand figure, which then propagates around the arc of the concentric gravity wave generated by the convection. So the previous simulation was for a single convective plume, and here's an entire storm. So in the top left you have the precipitation rate coming from the thunderstorms, and in the other grey figures you have the gravity wave response at different altitudes. So 15 kilometers, 55 kilometers, 70, 100 and 130 kilometers, and you can see how complex this wave field becomes as you have all the multiple plumes from the waves, from the storm generating waves, which then interact, and you get a lot of wave breaking and merging of phase fronts and interference between the gravity waves as they propagate up into the atmosphere. So this figure from Hoffman et al. In 2013 shows the distribution of gravity wave sources across the globe. This is taken using the AIRS imager and measures the sources in the stratosphere. Each of the panels in the figure represents a collection of months over the year, and this is for the daytime pass. So you can see particular hotspots over the world. So for example, in the tip of South America, over the Himalayas and Northern Europe, you get these sources from mountain waves, essentially, and you also get these convective sources associated with the storm tracks and also over North America. One problem with these sorts of climatologies is that they are limited to the time of day, or they're biased by the time of day with which the instrument takes the measurement, and also by the biases in the instrument itself and which portion of the gravity wave spectrum it is sensitive to. So now let's talk about the life of gravity waves. So gravity waves, when generated from their sources, they propagate into a varying background atmosphere at a variety of angles. And the distance that they can travel depends upon three parameters. First, the wave parameters themselves, i.e. the wavelengths and the frequencies. Secondly, the amplitude. And thirdly, the ambient atmosphere, so how the winds and temperature vary along the wave propagation path. And these varying atmospheric conditions can have three main effects on the gravity waves. That is refraction of the waves, reflection of the waves, and ducting of the waves as well. So first let's talk about refraction. Both the wind and temperature act to refract the wave. So if we look at the dispersion relation on the left hand side, you can see you have this n squared term and the u bar term. The n squared is proportional to the temperature gradient, and u of course is the mean wind. So if we assume that these background wind and temperature is varying with altitude, i.e. a function of z, then we end up with a vertical wave number which is also a function of z. So the vertical wavelength is changing with altitude dependent upon how n and u bar change with altitude. So how does this work? Well, if the wind or n increases with altitude, then the vertical wavelength will decrease with altitude, and this will make the wave propagate more horizontally. Vice versa, if the wind or n decreases with altitude, then the vertical wavelength will increase and the wave will travel more vertically. So here is just a schematic showing what would happen. So here we have a wave propagating up and to the right, and you can see as it encounters this wind which is increasing in the direction of wave propagation, then the wave is refracted to smaller vertical scales and more horizontal trajectories. So in this case we have a wind which is opposing the wave propagation direction and increasing with altitude, and here the wave is refracted to larger vertical scales and starts to propagate more vertically, as denoted by the red arrow in the group velocity. So now let's look at reflection. If you examine the dispersion relation again and pull out that k-squared term, there could be a case where the numerator and the denominator of the dispersion relation are equal to each other, and this essentially means that the intrinsic frequency of the wave is shifted to the buoyancy frequency of the atmosphere. And when that happens, the vertical wave number goes to 0 and the vertical wavelength goes to infinity, and this is known as a turning point level where the wave will reflect. Above this level, the wave is evanescent and cannot propagate. So just to give you a more intuitive visual idea of how reflection works, imagine you have a gravity wave which is propagating in the direction of the red arrow, upward and to the right, and it's propagating into this opposing mean wind which is increasing with altitude. So as it propagates, it will be refracted to larger vertical scales and larger vertical trajectories, and eventually it will hit a point where the intrinsic frequency of the wave is equal to the local buoyancy frequency of the atmosphere, and here it cannot propagate upward anymore. The vertical phases are completely vertical and the wave will reflect. As it does so, it will then go downward and to the right and will go into a decreasing opposing mean wind and will then refract to more horizontal trajectories. So this is a figure from a simulation I ran of a packet reflecting, and it's evolving from top left to bottom right here. And the packet is propagating up to the right, and the arrows and the Gaussian shape represent the mean wind. So you can see that what happens is that when the wave packet hits the reflection level, you actually get, in reality, a reflection and transmission of the wave. And this occurs because the wave packet is actually a spectrum. It's not a single frequency and wave number, and only part of that spectrum meets the condition to reflect, whereas another part of it will actually not reflect and be transmitted up into the atmosphere. So in this respect, the reflection layer can actually act like a filter for waves, allowing certain frequencies and wave numbers to transmit rather than be reflected. So this can lead to the concept of ducting. If you have two turning point levels in the atmosphere, with a region in between where a wave can propagate, the wave can become ducted. So let's look at how this works. Imagine you have an instant wave coming up to a reflection level or a turning point level. Then, as in the previous example, you'll get a partially reflected wave and a partially transmitted wave. But as that transmitted wave hits the second turning point level, it will be reflected again and then will bounce off the first turning point level, and you'll get this stuck wave which just bounces between these two turning point levels. And what that actually allows for is the facilitation of long-range propagation of waves that normally would not be able to propagate large horizontal distances. It's also key to note that these ducts are leaky, so you'll get energy leaking out of these ducts at each time the wave reflects off one of these layers. So this is just a simulation of a leaky duct that I performed. The wave is propagating upward and to the left initially, and the black lines represent the duct boundaries. So you'll see as the wave propagates, you'll get reflection and transmission each time that it hits one of those black boundaries, and part of the energy will leak from that duct up into the upper atmosphere. But so this is a method by these short period waves can actually travel large horizontal distances and distribute their momentum and energy far away from the source region where the wave itself was generated. So now that we've talked about the life and the propagation of the gravity waves, let's talk about their death. So in general, there are three main mechanisms that waves can end their life. Firstly, critical level filtering, secondly by wave breaking, and third by viscous dissipation. It's key to note in all three of these cases, either part or all of the wave energy and momentum will be deposited into the mean flow, and all three of these mechanisms are actually likely to generate secondary gravity waves as a result. So let's start by talking about critical level filtering. So if we examine that dispersion relation again, there's a point where the denominator, this omega minus UK, can go to 0. And when it does so, the vertical wave number goes to infinity because you're dividing by 0. And so the vertical wavelength actually goes to 0. This is known as a critical level, and the wave is absorbed into the mean flow. In reality, this actually happens where the phase speed of the wave, omega over k, is equal to the mean flow. So if you get an altitude level where the phase speed, the horizontal phase speed of the wave is equal to the mean flow velocity, then this will happen and the wave will be critical level filtered. So this is another simulation similar to the reflection one, except this time the mean wind is in the direction of the wave propagation as opposed to opposing it. Again, we're evolving from top left to bottom right. So you can see as the wave propagates up and to the right, it encounters this increasing mean wind and it starts to be refracted to smaller and smaller vertical scales, and eventually it hits this critical level where the mean flow is equal to the phase speed of the wave, and the wave itself is absorbed into the mean flow and will actually accelerate the mean flow here. So now let's go on to talk about wave breaking. So if you recall, a wave's amplitude will grow with altitude as it propagates upward due to the decrease in background density. But of course, the wave's amplitude can't increase forever. And eventually, the wave amplitude will grow so large that the wave will steepen. And what will happen is the peak of the wave, essentially the horizontal perturbation velocity, will overtake the phase speed of the wave. So the top of the wave sort of overtakes itself, and you get this breaking of the wave, this overturning of the wave. And this is known as the saturation point. And the saturation point occurs when the horizontal perturbation velocity is equal to the wave's intrinsic phase speed, as denoted by the equation in the bottom left. So here is just a simulation of this effect, and the wave will start in the bottom left and propagate upward and to the right, and you will see from the color bar on the right hand side the wave is increasing in amplitude as it goes up, and as it gets up to the top here it will start to steepen, and then the wave will cascade into breaking as it meets that condition where the phase speed, intrinsic phase speed, is equal to the perturbation velocity. So another way of describing instability in the atmosphere in general is the Richardson number, which is made up of the buoyancy frequency on the numerator and the wind shear in the denominator. And if the Richardson number is less than a quarter, this implies unstable conditions. The Richardson number describes two types of instability. The first is a convective instability driven by if n squared turns negative, and what this implies is an inversion of the density, where you have higher density over lower density and the atmosphere will become unstable in order to correct itself. The second is shear instability, which is when the vertical wind shear is large enough that it overcomes the tendency of a stratified fluid to remain stratified, and then Kelvin-Helmholtz instabilities and vortexes will form as shown in the bottom right hand figure here. So the n squared and the shear term that make up the Richardson number have both mean state and also wave components as well, and you can see they're dependent upon the amplitude but also the vertical gradient of these parameters, which will bring out the m, or the vertical number, wave number, when you differentiate. So both of these terms will be proportional to the amplitude and the vertical wavelength of the wave. So if you get wave steepening, you're going to cause these larger temperature gradients and shears, which can drive the Richardson number to instability, but also shortening of the vertical wavelength leads to larger temperature gradients and shears, which again can drive the Richardson number to become unstable. The initial break-in scales are roughly proportional to the depth of the unstable region, defined by a region where the Richardson number is less than a quarter. So I'll just show the simulation here. On the left-hand side you have the temperature perturbation of the wave as it propagates upward. On the right-hand side you have a vertical cross-section on the white line, which shows three lines. The blue line is the wind, the purple line is the temperature, and the red line is that Richardson number. So as the wave becomes steeper, the Richardson number approaches the yellow line, which represents the unstable point, and eventually the wave will become unstable, as you see there, at about 110 kilometers, and that is bounded by where the temperature gradient is maximum, as denoted by the purple line, and at the bottom end by where that wind gradient, the wind shear, denoted by the blue line, is also maximized. So from here you can see on the left hand side that the wave becomes unstable, will break and cascade into ever smaller and smaller turbulent scales, which will then be dissipated by the molecular viscosity when they get to a certain small scale. So now let's talk about viscous dissipation. So kinematic viscosity and thermal diffusivity increase exponentially in the atmosphere, and the values become significant in the thermosphere. So you can see the kinematic viscosity here on the left and the thermal diffusivity on the right, and they're both inversely proportional to the density, which decreases with altitude. So the amount of dissipation that occurs for a given gravity wave is dependent upon two factors. Firstly, the magnitude of the local viscosity, and secondly, the vertical wavelength of the wave. So you can see from the diffusion and heat equations here that they're proportional to the second derivative of z, which brings out this m squared term, which is the vertical wave number. So what this really means is that viscosity will act to damp small vertical wavelengths more rapidly than waves with large vertical wavelengths, and this translates into the fact that you'll have smaller vertical wavelengths dissipating lower in the atmosphere, whereas larger vertical wavelengths can actually propagate higher into the atmosphere before they dissipate. So if you look at a vertical wave number spectra with altitude, you will see ever increasing vertical wavelengths as you go up into the viscous regions of the atmosphere. So actually all waves die from viscous dissipation eventually. If you remember with critical levels, we said that they're refracted to increasingly small vertical wavelengths and then absorbed into the mean flow. But from the previous slides we learned that viscous effects act to dissipate waves stronger if they have smaller vertical wavelengths. So what's really happening here is they're refracted to smaller vertical wavelengths. Viscous dissipation is becoming stronger and dissipating these waves. Secondly, waves that break will cascade through turbulent processes to smaller and smaller scales, and then eventually they'll get small enough that again viscous dissipation becomes strong and will dissipate these waves. And thirdly, waves that survive critical level filtering and breaking will propagate up into the thermosphere, where the molecular viscosity and thermal diffusivity is very, very large, and they will just be dissipated naturally, and typically the ceiling on this is around 300 kilometers. It's also key to note that dissipation is accompanied by the momentum and heat flux diversion, or the deposition of the energy and momentum, and this can create mean flow forcing and heating or cooling of the atmosphere, and it can also, as a third process, generate secondary gravity waves. So secondary waves can be created by two main mechanisms. The first is the linear response, and this occurs from a packet scale dissipation, which leads to a body forcing over the packet scale and dissipation period and generates larger, longer period secondary waves. So you can see this wave packet evolving from left to right. The amplitude of the wave becomes smaller and smaller as time goes on. The mean flow is forced as denoted by the blue arrow, and the wind is accelerated in the direction of the wave, and then these secondary waves are generated which have longer periods and larger scales than the original. Second is the nonlinear response, and this occurs from wave breaking and wave-wave interactions, and these create very localized transient forcings which generate secondary waves which are actually smaller and higher frequency than the original breaking wave. So here's just a simulation of a secondary gravity wave generation by a breaking mountain wave. So you'll see this wave propagate up. It's actually hitting a critical level at about 90 kilometers. 80 kilometers, and then you see this wave breaking, these small scale structures form, and then these secondary waves appear above 100 kilometers, and those actually break again at larger scales and generate even further waves, such as tertiary and even higher order waves as well. So I'll finally talk about some of the current problems in gravity wave research. The first one is still having a good description of the source distributions, their intermittency, and what spectra of waves are generated from these sources in general. This is still not well known. We have these satellite studies, but again they suffer because of the temporal resolution of satellite images. They move over so fast and they sample a single point maybe once or twice a day, so you don't get any sense for the evolution of these sources. Secondly, because gravity waves are deep, i.e. they occupy almost the whole depth of the atmosphere from the ground to the thermosphere, it's very hard to measure the distribution of their momentum and energy and how they deposit those throughout the atmosphere. You really need a large suite of instruments which can measure the whole depth of the atmosphere to do that. Thirdly, how do these waves evolve non-linearly? So most of the theory is a linear theory, and we don't really have a very strong understanding at this stage of how non-linear evolution, such as wave-wave interactions, wave-mean flow interactions, turbulence generation, and a secondary wave generation work, and what spectra that they produce. They can't be well predicted at this stage. Fourthly, what are the effects in the ionosphere? To do this, you need to couple the neutral atmosphere with the ionosphere, and we know that there's these traveling ionospheric disturbances, a subset of which corresponds to the manifestation of gravity waves in the ionosphere, but they can also possibly produce effects like the ion outflow and also seeding of things like equatorial spread F. But really we don't know. This is a topic of research that is only beginning to be fully explored. And all of these really feed into the parameterization in general circulation models, which at the moment are poor. They need to prescribe a source distribution throughout the atmosphere and also an intermittency, which there's been some strides into this, but in general it's still not well understood. Again, you have instantaneous propagation of these waves from their sources to the wherever they deposit their momentum, which is crudely described by linear theory. There's not any consideration of non-linearity in these parameterizations, and also they're confined to a single column. So if a gravity wave is launched within a single cell in the GCM, then it stays within that cell, and you don't get any description of the horizontal propagation of these waves. So these are all big problems that need to be solved in gravity wave research, and hopefully upcoming missions, for example the ALL mission, which is going to look at the mesosphere, the temperature of the mesosphere using AMTM imagers from the International Space Station, might start to answer those questions, along with satellites which are measuring the thermosphere, such as ICON and GOLD, the thermosphere and the ionosphere. And really you need sort of systems level approaches to these problems. So you need a suite of instruments in conjunction with models which can span across multiple scales, from the global scale down to the very smallest turbulence scales, in order to describe these processes. So there really is a lot of work to be done, and I hope that this talk has given you some interest in gravity waves, and perhaps you can pursue and solve some of these problems. So I thank you for listening to this talk, and I'd like to leave you with this wonderful simulation by Hanli Liu et al. In 2014. This is from the Wacom GCM, and this is a high-resolution GCM run with part of the gravity wave spectrum resolved, and you can see how complex this wave field is over the globe, and this really is just a beautiful simulation that shows how much there is to understand about gravity waves in the atmosphere. So I thank you for your time and welcome any questions.